Good morning. Thank you all for coming, and thank you to Location Sound for putting this all together for us. We know that the subject of today's, discussion is of great concern to you, and hopefully the one thing you'll gather from this after you leave is that anything that boring just can't be that threatening. So I hope you've all got coffee. You're going to need it. At any rate, RF, what's next? That is a big question that we've been running into. We've always liked to start out with a little presentation of the first patent for a wireless microphone in England, 1917. It was called wireless, but it really wasn't. All the actors had to trail around with small wires hanging out from under their costume to the metal plate on the stage. I'm not sure if that was power or audio. It was a little scary. I'm going to give you the summary first. Right now, it is as bad now as it's going to get. Right now, we're existing with every television station in the United States transmitting on double the bandwidth that it really needs. They've been forced to go to the digital transition. So they're broadcasting on NTSC and they're broadcasting on ATSC. They're two signals. And it's costly for them. They're having to fund the power to two transmitters. And of course, the transition for equipment and so on is nailing them. This all began quite a long time ago, back in the mid-90s. In fact, this became law in the Balanced Budget Act of 1997. This was a budgetary thing. The FCC was directed to reallocate spectrum, use the new promised golden land of digital to use less spectrum for television broadcast, and then they were going to sell off all the frequencies above 700 megahertz. So it was really part of the Balanced Budget Act. The FCC is the only federal agency that's brought in, besides the IRS, that's brought in more money than it's spent. So after February 17th, there's not going to be any more analog broadcast in the U.S. I'm sure you're aware of that, although some studies indicate that about 21 million Americans will still be completely unaware of the transition and wake up February 18th and have no TV. And then we're going to transfer the 700 megahertz band to the new owners. Anybody know why it's February 17th? After the Super Bowl. You do not want riots in the streets if you shut down broadcast the day before the Super Bowl. So a little bit scary there. So what happens on February 17th is we get what's called the digital TV transition, and it is create FUD. Fear, uncertainty, and doubt. And that's what's hitting you guys. That's what's hitting a lot of folks in the various industries that use wireless microphones. There are two issues at stake here. And the problem is the information out there has gotten so cloudy that a lot of people don't realize we really are talking about two completely separate issues. The first one is the digital dividend. That is the sell-off of the white space above 700 megahertz, so the spectrum, not white space. See, even I'm doing it. White space is another issue. So what we're going to try to do today is clarify those two issues and get them straight on that point. And Larry's going to spend a lot of time actually getting into the nuts and bolts of what exactly the white space regulations are going to mean to you. The digital dividend, we've sold off the channels above 700 megahertz. There were some auctions run in previous years. And basically the buyers have been Qualcomm and some of the other telco companies. They've spent several $1 billion buying this space. And in theory, that's going to be used for the important communication stuff like being able to download your latest football scores on your cell phone. And they need more spectrum for more cell phone-based services. Larry and I get a kick out of the fact that what we're doing here is selling off television broadcast spectrum and moving everybody down into TV broadcast so that people can watch high-definition television at home, and then we're going to sell off this other spectrum so you can watch low-definition television on your cell phone. You know, that's really the benefit we're going to pick up there. It affects us because what's going on is we have to, as a manufacturer, we are going to be required by law to stop manufacturing wireless for U.S. sales above 700 megahertz because our manufacturing license allows us to build Part 90 and Part 74 products and they will no longer be Part 74 products after February 17th. So we reined it back in about a year ago and just, really cranked it back. And at this point, I get any orders above 700 megs. We're asking for a written sign-off that says, I understand what's going to happen with these. So it affects all wireless manufacturers. Part 74 is the part of the FCC code. And that basically regulates broadcast and motion picture use of spectrum. It is what you guys operate under. And it covers 174 to 216 megahertz. That's the VHF bands. Remember the old CR185s that operated in that range. And it also governs the 470 to 806 band currently, and it will stop at 700 megs, actually about 698 megs after February 17th. Currently, if you are going to be a user of wireless microphones or any type of transmission system in this industry, you have to be, first of all, involved in motion picture and television production, which you all are. And you are supposed to be licensed, and I know that's not the case. In fact, the vast majority of wireless microphones out there aren't licensed. In fact, I think I can name one guy in this room. The question is there going to be... The question is, has there been policing of the licensing requirement, and will there be in the future? And the answer to that is probably not. Now, I'm guessing what the FCC is going to do. They'll probably get rather aggressive above 700 megahertz because Qualcomm is going to be very jealous of their $10 billion acquisition. But below 700 megahertz, there hasn't been policing because, quite frankly, the FCC doesn't have enough bodies to cover it all. And remember, you guys are pretty... you're not an attractive target for them because legally you should be able to be licensable. There's a lot of people that are not, and there's a lot more of them than there are of you. Got another slide coming up. In fact, it says right here, until the proposal this August 2008, was when the FCC first came out with the current proposal that is now a ruling and order. And the proposal in August was we are going to shut down everything above 700 meg. Up until that point, they were very unclear. If you called the FCC and said, what's going to happen above 700 meg, we got a variety of answers, but the general indication until this point in time was that they were going to just let wireless mics above 700 megs operate on a non-interference basis. As long as there wasn't something in the spectrum, it was okay to keep going. They changed that in August. That was a ruling first proposed in August, ruled on November 4th, and that was a big change in the direction they were heading. And that was pushed by a couple of large organizations that were ad hoc committees, one called the Public Interest for the Spectrum Coalition. And that is a group that represents itself to be representing the consumers of America. But if you examine very closely who's on the board of directors and so on, you'll find the chairman is the CEO of Google, who wants part of this spectrum, and the telecoms. It's really kind of a skewed committee, and they were trying to put themselves in the public interest. They want to give access to the spectrum. The purpose is, and we'll talk about that when we get to the white space side, but that's what was being pushed. They want to get all you illegal users out of there. And so basically, at this point, all wireless above 700 meg has to vacate after February 17th. And there are penalties. So, basically they've said that's the way it's going to be, so that's the way it's going to have to be. Just some notable unlicensed users or unlicensable. These guys can't even get licenses because they are not, unlike you, they are not involved in motion picture and television production. So among them are the United States Senate, Kennedy Center, NASA, Broadway, of course. All those theaters on Broadway were basically operating outside the definitions of Part 74. Darn near every church in the United States that has more than about 100 members, because some churches heavily rely on wireless nowadays, and interestingly enough, Google. So there are a lot of unlicensable users. The estimate, I've heard estimates ranging from 1.5 to 2 million unlicensable users, people that did not ever qualify for wireless applications. So are you guys licensable? The answer is yes. You are involved directly in motion picture and television production. And if you are involved in broadcast, you can even do the 944 to 952 range, but that's only if you are involved, like John here, in broadcast. But if you're only in motion picture and television production, you're developing content, but you're not a broadcaster, then you can have basically everything in Part 74 except 944 to 950. Now, the process for getting a license right now is in place. Again, that's that Form 601 and Schedule H, which I got to tell you is really arcane. One of the problems in the licensing process was over the years, the process didn't change with the technologies. Part 74 was written before wireless microphones were practical. You know, there were wireless microphones, but they weighed a lot and they were huge and they were really not practical for your type of work. And so there are things on the form like the altitude of your antenna and the geographic location of your antenna. You know, what is your longitude and latitude for your antenna? Well, it depends on whether the actress is over there, but you're going to have to pick something, maybe pick something in the center of your zip code. But yeah, it was never really properly set up to handle it. The other thing it doesn't handle well is the frequency. It doesn't take frequency agility in wireless microphones into account at all. It's asking for a single frequency on the form. Wireless microphones are a non-proprietary broadcast. Even with a license, you can't interfere with other signals. So if you get a license, it basically says you're allowed to use it, but don't cause anybody any trouble. So it was kind of a single-edged sword, you know. Okay, white space issue is separate from the digital dividend. It's about what's going to happen after the digital dividend and what's going to be used with the, quote, unused space. And this is a spectrum that I took. This is New York City. Sorry, I should have done LA, but I did New York. And but this is what New York currently looks like before. All the blue lines here represent an NTSC broadcast, an analog signal. And all the wide yellow bands represent digital signal. Before and after, this is basically what we're dealing with here. We're a before and after section. So basically all your digital TV comes up. The white space is all the little empty spots that are so-called unoccupied bands. And they're going to get about 120 megs open in New York City, for example. So this is what causes... Boy, I tell you. Okay, I'll have to tell you why I'm losing it here in a moment. White spaces, at any rate, in New York, we're losing this spectrum. All these guys were thinking, this spectrum is free. This is what Google and Microsoft and Apple and all the computer guys are looking at, saying, we really want this chunk of spectrum because, look, it's all empty. It's unused. It should be made available to the public. But this is what's really happened. This is what you get with a single Broadway show. This is coordinated for comms, in-ear monitors, and wireless microphones. So what you've got here is blue lines are the primary carriers for the wireless. Red is the intermod products. And this is a single location. This is what you would get in a frequency coordination for a... Now, this is a working system. It looks terrible in terms of all those little red intermod products, but they're down low. They're not really causing a problem. But if you look at all those blue lines, that's the wireless in use on a single Broadway show. Okay? And this is what the white space advocates, the Googles and so on, are saying is unused spectrum. It's actually very well used spectrum. Properly coordinated, you can do this in one theater, you can do something slightly different in another theater. Remember the proximity issue you talked about. You know, we got a 400-foot radius, so the theater next door has to watch out for this, but the theater next door to that one doesn't. And of course, you've got the walls and the bricks and the buildings themselves attenuating it even more. So it makes it possible for all these Broadway shows to do this. But if you throw a cell carrier on top of all this or some other equipment, it'll mess up the coordination. Makes it a real difficult factor. So the issue is computer equipment manufacturers are looking at this and lusting after this spectrum because, after all, everyone who has a wireless in that space is illegal, quote unquote. So they have no rights, therefore it's not used. Now here's the sticker. Because nobody that was a legal user was registering their wireless microphones and getting their licenses, when the FCC did a database search of wireless mics to see how many licenses there were in the United States, they found 937 licenses, most of them owned by television stations. 937. That was it. There are only 937 wireless microphones in the United States, according to that database. And of course, that's not that. Those are guys that had licenses. Now we know that there's probably more on the order of 2.5 to 3 million, but you know, it's another story. What they want is access for things like wireless routers. Perfect example is, you know, in a home network. You want to put a wireless network in your home. My house is traditional wooden stick, you know, stick and stucco type construction, drywall on the interior. And a typical wireless router like I have operating in my house at 2.4 gigs works quite well because it's all short range and it's wood construction. On the other hand, Larry has a house that's actually made of adobe with walls this thick inside. And they're made out of basically mud and, you know, hardened dirt. And, you know, poor Larry, he's in a dirt house. And, but the problem for him is if he takes he's got a wireless router as well, but in his house, he can take his laptop and see a real high bit rate here, move it over to here, just enough to get it past the corner of that wall, and it'll drop out. He'll lose his signal. So for Larry's application, a wireless on this lower spectrum, which has better penetration power, it's an ideal spectrum for this type of application. It makes sense to develop wireless routers to use this piece of spectrum, and that's what they're looking for. And they have been marketing it and presenting it to the FCC and to the federal government as, and this is a direct quote, Wi-Fi on steroids. That's how they view it. That's what they want it for. And Adaptrum, Microsoft, Motorola, Philips, and Google all have plans. Google's got its Android platform that it wants to get out there. Just to repeat in case you didn't hear it, John was saying that a lot of people were not licensing their own wireless because when you're on contract under a broadcaster, you're working for NBC News or CBS, ABC, whatever, that your equipment would fall under their broadcast license. So, you know, it made good sense not to do it twice, be repeatedly redundant again. So right now, there's no technical resolution on the white space. What's going on with the white space devices is, first of all, they came to the FCC and they said, well, we can build wireless that will do a scan of the spectrum. And if there's something already on the air, we won't use that frequency. We'll avoid it. And then we'll just go to another piece of spectrum and just we'll make smart devices that won't cause problems. And unfortunately, they have not yet convincingly built a product that does that. They've been through 2 series of tests now with the FCC and failed both times. Yeah, they failed to not only detect interfering sources, but they also failed to not interfere with digital television, which is the FCC's biggest concern. They don't want people bringing this stuff into their home and taking, you know, 5 houses in the neighborhood off the air on their DTV high-definition broadcast. So they have not yet technically been able to develop a product that meets this specification. So that's kind of an interesting development. But the good news, and Larry will get more into this, but the good news is that they have failed to develop this product. They really can't make this, but the FCC said, okay, we will work with those ideas. You'll have to be spectrum sensing, and you're going to have to avoid local interference. So that's a good news part, and when Larry gets into the details, you'll see why. So the new ruling, just a basic rundown, and Larry will do the detail work here, is white space devices are going to be allowed. And they must either detect the spectrum, they have to be able to scan and do a detection of the spectrum and go out and scan and see if there's something, or they need to go, many of them will need to go to a geolocation database. Now that hasn't been determined. Who's going to manage the database, how that's going to be done. In the proposal, it looks like it'll be some third party. But basically, you register, like John here would take all his wireless microphones and register their use and frequency for the lot here in Burbank. And that would go into the database and would say basically, we have wireless operating at this geophysical location, therefore you cannot operate within, what is it, a kilometer? Within 1 kilometer of that device. So you can build a database now that these devices have to access, and then they basically are told, thou shalt not go here. There are registered products. The idea behind that was to protect large-scale events like the Super Bowl. You know, the Super Bowl typically has in excess of 200 wireless microphones in operation during a production that they have to coordinate. And they can't afford to have some wireless router knocking the main act or the referee or whoever off the air. So by going to a geolocation database, you can go in and say, we're going to be using these wireless over this time frame. And then the devices are supposed to go online on a regular basis and check this database and adjust themselves accordingly.
So you can update it over and over.
You can update it over and over and over, exactly. Channels 21 through 51, they're going to limit to 40 milliwatts if they are operating in the TV channel adjacent to a DTV broadcast. So adjacent channels to DTV, they're going to be limited to 40 milliwatts, and if it's a piece of TV channel that is free on either side of other television broadcasts, it'll allow up to 100 milliwatts. And those are, and then also there will be channels 2 through 51 will allow what are called fixed devices, and the fixed devices are units that are, you know, located in a solid location, not portable like a cell phone type or similar device. The fixed devices will be limited to 4 watts radiated power. And again, they have to reference the database as well. All these devices have to go to the database and say, is there something operating in my vicinity I have to avoid, and then set itself accordingly. Then it also has to scan the spectrum. Some of the portable devices are exempted from scanning the, going to the database, but they have to report to a device that does scan the database and reports back to them. It's a complicated requirement. All the specifications in this, what Larry is going to be talking about later, has only to do with the white space requirements, and they're tough. They're really hard. So we'll get more detail into that. Another thing they're going to do is they're in 13 markets, which of course this is one of. I guess they consider LA a major market, not Albuquerque. I don't understand. But in the major markets, the 13 major markets, there are frequencies that are going to be used for emergency applications down in the 470 range that are already in use here. And what they're going to do is also reserve a couple of bands in up around channel 36. Channel 36 is right now reserved for radio astronomy. We're looking for ET on that spectrum because everybody knows extraterrestrials broadcast in that spectrum. So what's happening on either side of that is if there's a blank, the closest adjacent channels, TV channels, to that spectrum will become reserved for wireless microphones, for example, here in LA. So when we look at the LA spectrum and let's say 34, 35, 36, and 37 are occupied, 33 and 38 would be reserved for wireless microphone use in LA. And don't write that down because I'm just winging it on those numbers, but we'll get that information posted so you know what to avoid. But again, that's reserved for wireless microphone use, and I think they're thinking more in terms of the non-Part 74 users, the churches and the so on. The problem is the FCC hasn't clarified yet the licensing issue for the non-Part 74 users, the churches and the bar bands and the schools and the universities and the government themselves. And I was recently in a phone call with all the major wireless microphone manufacturers through the Professional Audio Manufacturers Association, where one of the things we're going to ask the FCC for is some clarification on the non-licensable users. You know, those people need to be told what they can and cannot do, and it's not been clarified. You guys, it's clear. You're motion picture and television production. You are Part 74 users. You have absolute right to the spectrum. Another nice thing about the new ruling is that testing is supposed to be more vigorous with sensing-only devices. In other words, you've got to make, they are going to increase the rigorous amount of testing when it's a sense-only type device. It has to pass their testing even more rigorously than it would if it was one that could also access the database. So they're making it very tough for these white space devices to operate in our spectrum. And that's the good news. And we'll get more into that. Like I said, hang on for Larry. He's really been reading the FCC proposal. And every time we read it, it gets better and better. So the white space result, in a nutshell, like I said, I'm giving you the summary first, and then Larry's going to give you the details to justify the summary, but it's a site management issue. White space devices are not going to be these heinous, high-powered broadcast entities that are going to be blanketing Los Angeles with loads of RF and blowing everything off the air. You already have that now. That's the combination analog and digital broadcasts that are hitting you hard, because that's sucking up a lot of spectrum. Come February 17th, all those high-powered NTSC broadcasts go off the air. You're going to see a lot of spectrum freed up. And what will eventually, and again, there are no products that exist that meet the white space specification at this point, eventually these things will start cropping up. But it becomes a white space issue. You know, Mike, if you don't want this stuff interfering with you on the Warner lot, don't buy it. It's a matter of don't install it in. But the problem is it's going to require bringing in those other guys from the really dark side, and that's the IT guys. The IT guys have to be made spectrum savvy. They need to be made to understand what's going on with your productions, that you are using this spectrum for your productions. IT at Warner and at Universal and NBC, you've got to make them aware of the fact that they can't run out and buy this new Wi-Fi on steroids box and willy-nilly plug it in. In the past, because all that stuff was at 2.4 gig and 5.1, it was a plug-and-play issue. You just went and bought the box, you brought it in, you plugged it into your network, and you had it up and running. You didn't have to worry about slamming somebody else. But now, if they begin developing boxes in the spectrum, it becomes an issue of people have got to communicate. Site managers, you know, and now for you location guys that are traveling around, it means you're going to have to alter a little bit what you do when you arrive on site. You can't pick a frequency that always works in LA. You're going to find lots of frequencies are going to work in LA, but they may not work in this spot. You may have to change to a different frequency in this spot because they have a device that's operating on channel 37 in this location. And you go down the block and get 400, 500 feet away, and that no longer becomes an issue because it's low power, it's local, and down the street there'll be another piece that'll be open up and maybe another piece that'll be closed down. It all depends on how ubiquitous they make this. But I don't imagine we're going to see a situation worse than what we have right now. Right now you're battling kilowatt outputs from television stations that are flooding the valley and flooding the mountain regions around here. And when those go off the air, that's going to give you some considerable improvement. This is a slap. Okay. I'm going to have to fess up here. I'm going to skip ahead a few slides, because then you'll understand what's going on. What I'm demonstrating right now is a thing called FM capture. The FM capture effect is if you have competing interference a few decibels below your desired signal, you can bury that signal in your noise floor, and you won't even know that that interfering signal is there. I deliberately put my transmitter on an interfering signal to demonstrate this capture effect. And basically what's going on here is this is a NTSC broadcast channel in Albuquerque, New Mexico. This is what the spectrum looks like. And if I fire up a transmitter relatively close, like 20 feet away from my receiver, this is what it looked like. Basically, I was 10 miles away from the NTSC broadcast. So you can see I've got a fair amount. I've really pretty well buried it. This is my wireless transmitter at 100 milliwatts at 20 feet. This is the NTSC broadcast, and at 20 feet, you're never going to know the NTSC was there. But as you increase your distance away from the interfering source, here I moved it to 75 feet. I actually walked the transmitter down to Larry's office. And so at 75 feet, you can see the difference between the two signals is now considerably reduced, because the television broadcast is going to be right on top and it's going to stay static, whereas my power will decrease as I increase range. But FM capture can be used as long as you keep your antennas close. Sometimes you can bury in it. Now this is up against a 1.3 megawatt transmission. So, I mean, I was picking a worst case scenario, and that's what's going on right now. I'm in the middle of a television channel with this transmitter. And so it's effectively reducing my range a little bit. I'm a little more susceptible to the dropouts and so on that you've been hearing here when I move in a certain spot. There's one bad spot here. But actually, if that antenna was just a wee bit closer, I'd probably have a very good, reliable signal for the entirety of this thing. So if I move this out, will be able to improve my signal. But what's going on is I am basically in the middle of that spectrum. Here's another example, so in Albuquerque, and what we've got here are, I'm going to fire up two wireless on a DTV channel. You've got the DTV channel right there, and if we fired up two wireless on top of it, and this was at about 60 feet of range, so you can see it's a little more reduced signal, but we were able to operate reliably in the middle of an active DTV channel here. Now, the one thing I'm doing here is I am breaking the law. I am causing interference. When I did this demo at Infocom this year, we had a room about the same size as this, and I operated in the middle of a DTV broadcast the entire seminar. And we had a DTV receiver and monitor so people could see it, and as long as I was in the room, that signal was interfered with and basically locked up. Every time I turned on my transmitter, the signal just locked up, and that was that. And when I left the room and walked down the hall, I got about 200 feet away. Then my wireless dropped out because my range was reduced by the presence of the DTV channel, but the DTV came back on. So this action I'm doing right now is really not allowed. I mean, I'm put myself right on top of a television channel for demonstration purposes. You don't want to do this on location because you could really cause a problem. You could be interfering with somebody's TV down the, who knows, I may be interfering with a playoff game right now off, something going on a TV within a few hundred feet of us here. But that's what the FM capture effect gives you. And the reason I bring that up is it can become a strategy when you're doing location work. The closer you can get to your antennas, the more reliable. Power is what counts. We'll talk about that in a little bit. I got off track there because I wanted to explain all these heads. But for those of you here were here the last time we did one of these, I had the same problem, except it wasn't planned. So it was a little bit frustrating. Okay. So getting back to Albuquerque, this is what Albuquerque spectrum currently looks like. And underneath is a bar graph that comes off the Professional Wireless's frequency coordination program to show that they really match. This is what their program said should be on the air, and this is what was actually on the air. And you can see the DTV channels line up and TSCs line up. Everything just basically lines up as it should. The blue lines are the NTSC broadcast, the analog broadcast, and then these wider bands here are the DTV broadcasts. And so, for example, this DTV broadcast, that little spike right at the beginning, that's the pilot signal that helps the televisions lock into the digital content. And so it takes up the full, you can see it takes up that full 6 megahertz spectrum, whereas NTSC has got your chroma carrier and then your oral carrier here. And so you get this more characteristic two-spiked signal with a lower level signal for audio. So what we've got here is a representation of Albuquerque just as it is. If you take all those blue lines out, that's going to be Albuquerque in on February 18th. There's going to be a lot of these signals here.
Excuse me.
Yes.
Pull the mic cable away from your antenna. That'll help you.
Actually, it might help if I get my cell phone away from that too. We love cell phones. I just make them, okay? Yeah, and I should get the other sticking issue out of the way right now. Those of you here the last time, brought this up a number of times. I just want to make it clear right now, no, we don't have a Mac platform yet. Sorry, no Macintosh software. We've got a couple of ways to handle this. And again, frequency modulation is the primary method most wireless microphones use. It's got a lot of advantage. The transmitter centers on a particular frequency and basically deviates from that based on amplitude and frequency of the audio signal, and that's how we transmit to the other end. And the amount of change affects your amplitude and also your signal-to-noise ratio. One reason why we're always harping on get those transmitters hot, get a good hot signal going out to the far side. An FM signal is fairly straightforward in its spectral mask. It looks, it's a fairly clean, little tight signal that can be easily picked up. Communications radios use FM, and they tend to be narrower deviation, 2 kilohertz to 15 kilohertz. Combat radios are narrow deviation because they're trying to get a number of frequencies going together. And you know how good they sound. They have that nice, crisp, combat radio quality that, you wonder how they ever communicate. What? So deviation definitely affects the quality of the signal that you've got. Wireless microphones, assistive listening, and in-ear monitors tend to have deviation ranging from 15 kilohertz to 75 kilohertz, and that can be in both VHF and UHF, although most VHF tend to be narrower band. Our old CR187s and CR185s were 15 kilohertz of deviation, as well as CR1. Advantages to FM. It's not completely signal strength dependent. We are looking at the variance of the signal, not the amplitude like you do with an AM signal. So when you get out at farther range, it tends to hang in much more solidly. You can also get high channel density with FM. We've been able to do, for example, in New York, we have a studio at BC that has a really high frequency density. They've got 64 channels in a single studio, all with 100 milliwatt or quarter watt transmitters. 64 channels operating simultaneously right there in the New York broadcast area. So that's also a very crowded spectrum, very much like LA, and yet with an FM system, it was really actually quite easy to get that system up and running. And it's also got good resistance to low power interference, that FM capture. Like I said, I'm sitting right on top of the strongest interfering source I could find, and if I had that antenna a little bit, half the distance closer, I think that 3 dB would make all the difference. We've already covered FM capture. And this is what we were doing, the FM capture demonstration. Any questions about FM? Where we're at so far? Yes, sir.
Pre-emphasis, de-emphasis, and companding.
Pre-emphasis, de-emphasis, and companding. Those were required in earlier designs, largely because in an FM system, the FCC says thou shalt not deviate beyond X. And so we had to make sure that limited us to how much data we could get out on that broadcast signal. A compander is basically compression and expander. You're compressing the FM signal on a 2-to-1 ratio and expanding it on a 1-to-2 ratio on the receiving end. And the idea behind the compander was to give more dynamic range to the signal. If you were limited strictly to that without the compander in your audio, it really limited the dynamic range of the audio signal. Well, what the compander does is allows you to expand that. The drawback to the compander, as all you guys know, is that, or at least those of you that have been in business a while, is that the compander introduces audio artifacts. Our first compander was fairly straightforward. We used the same compander chip every wireless manufacturer was using. And that is a single band compander. It covered the whole audio spectrum. And so if you had something like jingling car keys, everybody says, well, that's not a fair test, jingling keys. Well, it is, because you can have similar type signals in an audio that you're trying to do on location, like cymbal. I tell you what, as soon as I finish with this section, we'll take a break. I'll get on to a clean frequency, and hopefully that'll clean it, because we're going to need it. The compander introduces audio artifacts. In the early 90s, we introduced the dual band compander, where we had 2 companders, and the crossover was at about 1 kilohertz, and that was the 190 and the 195 wireless. And there we had companders idealized for the the audio part of the spectrum. So we had something idealized a little bit more for the low frequency signals and one for the high frequency. And that got rid of a large part of the compander artifacts that we were dealing with. It left us with a couple that were still a little heinous. The car keys sounded a whole lot better because we had one idealized for high frequency, and the low frequency stuff was a lot more stable because of our low frequency. But there were still things. There's a sound mixer in New York, Jerry Alper, and Jerry used to call me up because he'd get these scenes with the method actors. I know your favorite. And for example, he had a scene with De Niro where he was on a gurney. He was supposed to be dying. So while he was dying, he was talking like a dying man. You know, he was barely talking like this, really low, and just could barely get anything out. So they had to crank everything up on the set. They had to soundproof as much as they could because they had to really crank the gain. And what was happening is every time De Niro spoke, he would speak a little bit, and when he stopped, there was that little, and you guys have heard this, that little whoosh in the background, that little ghost in the background. And so that was a compander artifact. And when you had very low gain and you had to crank everything up downstream to capture a very low level signal, it was impossible to get away from. And that was the holy grail, get rid of the compander. And that's where we eventually came into doing the digital hybrid system. We'll talk a little bit more about the digital hybrid in a little bit, but that's kind of where that's what led us to it, was to get rid of the compander. Do encryption issues. I really don't have that highlighted as something to delve into, but if you want to talk a little bit about encryption, we can do that. We do make an encrypted product that is primarily sold into people to want to keep secrets, like pharmaceutical firms, things like that. Disadvantages of digital is that a fully digital system has, we cannot get as high a frequency density. We do have a 700 series as a full digital system, and we cannot get as many channels operating simultaneously in the digital realm as we can in the analog realm. That's one of the big myths of digital. Oh, you can get a lot more going. Well, you can get a lot more going if you're doing an online, not streaming audio type environment like you do with the internet. With the internet, they have what's called error checking and concatenation. And if something happens bad at the receiving end, it can send back a message saying, I didn't get that, could you resend it? And it concatenates the audio stream and puts it all back together. And as long as that stream is fast enough, it can keep up with it. But you've all heard online audio that gets broken up if there's any kind of break. Well, we can't do that in the wireless side. There's no way to do error checking and say resend it again. Could you have that actress say that again? It just doesn't work. So it's also a current hog. Pulls a lot of DSP, digital signal processing, and that increases the battery use. It really pulls the battery down very dramatically. Most of the battery use in our digital hybrid is centered in the DSP side, not in the radiated power being broadcast out to your receiver, but really it's what's happening in the transmitter. So the range per milliwatt has not tended to be as good. Now we've been working on that, and there are some technological changes that we're affecting now where we're finally getting past that limitation. You ask about spread spectrum. Spread spectrum is where you spread the signal over a large spectral range to minimize the impact of interfering sources. And there's a number of ways to do it. Frequency hopping was one of the original methods that came up. The idea is to get away from interference. If you've got somebody trying to interfere with your signal deliberately, you want to get away from that. That started in the military realm. In fact, the first frequency hopping was developed back in World War II. And it jumps from channel to channel on a quasi-random basis. Basically, it says, we're going to transmit here for a little bit, and then we're going to jump over here and transmit for a little bit, and then we're going to go over here, and then we're going to go over here, and we're going to go over here. And by jumping around, it makes it hard for the other side to put up an interfering signal, the jamming signal that causes problems with interference. So here's your trivia question for the day. Who was granted for the first patent? Hedy Lamarr. The man is a winner. Interesting story behind this woman, and she was the wife of an Austrian arms dealer. You know, she was the arm candy for early in her life, and she attended a lot of meetings between him and people buying weaponry systems. And so she was actually quite a smart woman. She saw the writing on the wall before World War II began and got out of Europe, came to the United States, became a movie star, but she was actually quite smart, and she helped develop the first frequency hopping thing, she and a piano player. And the idea originally was to develop an interference-free of getting some player pianos synchronized so they would all play at the same time. And so when the war came along, she took this technology to the United States Navy and proposed that the Navy use it for guiding torpedoes. They wanted to come up with a radio-guided torpedo. Correct me if I get any of this wrong. Sounds like you know the story. And basically, the idea was to steer the torpedoes, and then the opposing sides, what little they had in electronics counter warfare at the time, couldn't jam the signal. And, they could see the torpedo coming and there was nothing they could do. They couldn't find the frequency they were broadcasting on and stop them from getting them. Unfortunately, the Navy really didn't use the technology during the war, but eventually she was honored by the Electronic Pioneers Association just a few years ago and given their outstanding, some outstanding achievement award for that. So anyway, it does involve basically hopping signals from one transmitter and back. And it got refined by the Israeli Air Force, and they were the ones who really got it into a very effective method of communications, and it makes it very hard for the enemy to jam. So spread spectrum frequency hopping also eliminates the need for frequency coordination because it allows you to just hop frequencies around. And if there's interference there in the military model, they have what's called a look-ahead capability. They go and they see is there interference before we jump. And if there is, we don't jump there, we jump someplace else. But they're only about 1/10 of a second on each frequency. I mean, it's hopping very rapidly. So as a result, even if you have interference, it's only for 1/10 of a second. There are a few problems, however, with spread spectrum for all its promise. One is Shannon's theorem. And Mike Reiner here got to sit in with us when we had a presentation on spread spectrum about 1995. Where we talk about it. Basically, Shannon's theorem, X amount of data can be transmitted over Y amount of bandwidth. You can only do so much data at a time. It takes a certain amount of speed. It's the sample rate, the word size, and the bandwidth that controls this. And professional audio, what you guys do is a lot more critical. You require much more bandwidth than military communications do. When we did some investigation into coming up with a spread spectrum product, and we did a lot of investigation into it. We spent a fair amount of money, brought in some consultants, and talked about it. We were looking at just for intercoms, and just to get intercom quality audio. The limit, we wanted to be able to get 16 drops, and it couldn't be done. So it very limited in the promise that was made out there. It looked good on paper, but in reality, once you did the math, you just couldn't get there from here. There's also some regulatory limitations. The FCC puts more limitations on civilian spread spectrum than there are on military. There is no look-ahead capability in the civilian world. We can't do that. We're required to hit all 50 frequencies. You have to use 50 frequencies. You have to hit them all. So you can't skip, oh, there's interference here. You can't look ahead and skip that. So another limitation on the thing. So the most common method being used in digital broadcasts is called pi/4 quadrature phase shift key, or QPSK. And that's what we use in our 700 series encrypted wireless. It has some advantages. It's kind of easy to implement. It's easy to suppress sideband interference. You can pass the carrier through a double balanced radio mixer and eliminate sideband sources. And it's orthogonal topography. It lets you change the modulation without getting a lot of AM vector in it. The AM vector is the thing that is the curse for all of us. These things. How many, that lovely sound you get, that's the AM vector in poorly grounded microphone elements. You guys have had a champion that you probably don't even know about, a consultant out of Chicago named Jim Brown. And he has been taking it to the microphone manufacturers about grounding issues in microphones. Because when microphones were first getting developed, there wasn't anything going on in this spectrum. There weren't components in the microphones that reacted to this spectrum. I mean, there was nothing going on. It was dead spectrum, nothing happening. And then cell phones came out with this wild AM vector, and it was getting into the fed elements of the microphones, your condenser mics and so on, and generating that noise. We got a lot of calls. I'm getting interference on your wireless. The wireless was fine. It was actually the capsule that was picking up the signal, translating it to audio, and pumping it down the line, and the transmitter can't tell between wanted audio and unwanted audio. If we had that capability, we could keep Washington completely silent. But when you have the FET element converting an RF signal, and the problem was grounding and shielding in the microphones themselves. If you are encountering problems, by the way, with that, I don't know how many of you are aware of it, but Neutrik makes a XLR connector series that is shielded very well. There's a ring of capacitors in it, and it has also ferrite beads that help reduce that problem from backtracking from your cable into the microphone itself. And it's the EMF series by Neutrik. Very nice little connectors that do a very effective job of reducing the RF interference coming off of a cell phone or other AM active source. And it'll help keep some of your microphones, some of your older mics quiet. Yeah, it looks exactly like a regular XLR connector. And you put it right on your cable. It hooks up basically in the same manner. It's just a little more complicated to assemble because there's more parts. There's the annular ring with all the capacitors on it, and the beads are already in place. You don't have to slide those on or anything. It's just basically solder it up, put it together, and it will knock things down. I attended a grounding and hum workshop in Chicago where they gave a very good demonstration of that with a very susceptible microphone. If you waved a BlackBerry or a Nextel phone anywhere near that mic, it went off. But when we put that cable on, we basically took away the antenna for the microphone because it was coming in on the ground, the shield. And we took away that pathway. AM modulation, it is not putting out a lot of modulation on the AM vector, so it has less of an impact on those susceptible microphones. And you get increased efficiency on the output stage. It's a pretty effective method for broadcast, and we are working on a new platform. Basically, we're working on a bag repeater system, 4-channel repeater in the 902 to 928 range that is a spread spectrum, not frequency hopping, but direct sequencing spread spectrum system that is using QPSK for the modulation method. And it works really nicely. We're finally getting past some of the flies in the ointment there. FSAM is another method. It has an advantage, no data compression, but it's more susceptible to out-of-band noise, and I'm not sure of anybody that's using it at this point, but you may hear it tossed around. What's the advantage of digital versus analog on RFI? Well, not a lot. And again, this is why we came up with digital hybrid. Again, we talk about that FM capture effect. Well, what's the susceptibility on the digital side? Well, digital systems require about 12 to 14 decibel signal-to-noise ratio to operate clearly without interference. FM can go much lower. FM capture effect is a lot more solid. If I had tried the little demonstration on FM capture, the dropouts would have been much more severe and really would have been totally unusable. So you can see that there's a real disadvantage in going to a full digital. We run some interesting problems when people try to run the digital system in these encrypted applications. There's boardrooms, for example, where they're trying to the Sarbanes-Oxley Accounting Act that came as a result of the Enron scandal puts new criteria on publicly held corporations about release of private information. You don't want people to get an advantage. So now they're being forced to go to encrypted wireless microphones in their boardrooms. And we have one boardroom where they're trying to get 24 of these up and running, and it's a nightmare. We just struggle with it constantly. Digital versus analog on the range. This is what we've been able to, if you're talking equivalent power output, this is what we've been able to get up to this point. Now, we've made some improvements on this. Things are improving. We're working it out. But when we first developed the 700 series, this is the range we were getting with the digital. This was what we were getting with analog, and then the digital hybrid was yielding the best result. The other thing in digital versus analog is latency. And of course, we've been through this already. We've kind of gotten past the learning curve on latency. But latency is, right now, for example, on the digital hybrid is 3.2 milliseconds. You have to process the data. And the controlling factor here is the digital to analog conversions that are occurring through the chain. They impart a latency to your signal. So in the time domain, it's the same effect as moving a microphone 3 feet further away from the source. But with the same amplitude. You're not losing level, but it is moving it out in the domain of time, about 3 to 4 milliseconds, depending on the product. And the only other thing about a pure digital thing is that you can encrypt it. And I'm not going to get into that unless you want me to. I don't know how much you run into a need for secret audio. Okay, let's see. That's, like they said, security is relative. Your relatives are not secure. Let's see. Any questions up to this point? Okay. Let's talk a little bit about the interference issues and how we can deal with it. Interference is the presence of another signal, something you don't want, sitting on top of the signal you do want. And how close that signal can get to your signal is very dependent on receiver design. Basic receiver architecture starts out with the RF hitting an antenna at the far end there, and then going to front-end filters, your amplifier, an oscillator that mixes in with the signal to mix it down to audio, into a lower wavelength, the IF section, which takes it even further down. Then you've got an FM detector. That's where the discrimination, the FM capture works. And then you get your audio section. And the whole key to the thing is right here in the front end. A good front end on a wireless microphone will reduce interference sources. This is where we concentrate a lot of engineering effort. If you get a very tight front end on the receiving front end of a wireless, you can get closer to an interference source and still operate without difficulties. And it is the heart of a receiver design. Make a tight front end, everything else falls into place. But it's not the only place you can affect it. You can also get good results elsewhere. This is comparative receiver front end filter slopes. And basically, when we talk about the front end of a radio receiver, we talk about the Q. A low Q filter is very broad band. It may cover a wide range, whereas a high Q filter is very tight and narrow. So the idea is to keep that Q reduced as much as possible. And if you take them into the real world, it kind of shows you what's going on. When you're dealing with wireless, you know, if it's an unused TV channel, there's nothing going on in there, a wideband unit's going to work just fine. But if you throw it into an NTSC broadcast, and remember that you're going to be dealing, if you're doing location work and you're going around the world, you're going to go to other countries. The United States is going digital. Some other countries are going digital, but there's going to be a lot of PAL and NTSC out there still on the air, and they look like this. And you're going to need tight front ends to get into those empty spots, the so-called slot frequencies. So we developed the tracking front end to help assist with that, where basically we have the receiver dial itself in. One of the problems when you go backwards and look at that front end issue, what if you're developing a wireless microphone and you want it to be frequency agile? It has to tune from this frequency to this frequency. Well, if you design the front end to cover that whole band, you've got a pretty wide open front end, what we call a barn door, you know. It'll let everything in, and it's going to cover the whole thing. So, and that was one of the reasons for years, and some of you go back with us quite a few years, and you can recall back when we had the 195s and the 190s, and we were the last guys in the wireless world with fixed frequency wireless. Everybody else had frequency agile. And you were saying, when are you guys going to come up with frequency agility? When are you going to come up with frequency agility? Well, the reason we weren't going there was because of that barn door. That was kind of counterintuitive to our philosophy of RF front-end design. And it wasn't until we came up with the concept of a tracking front end, where basically as you tell the receiver you're going to work on this frequency, that we would have it retune its own front end. There's a microprocessor on board, and it varies in technique from model to model, but basically the microprocessor retunes that front end so that as you change frequencies, it changes the tuning and keeps you with a narrow front end. But that took a while to develop. That's why we were kind of lastest on the market when it came to a frequency agile system. Another way we can increase the filtering in the system is to put real sharp filters in the intermediate frequency section after it's been mixed down. And we tend to use a variety of methods over the years. These are various types of filters. 6-pole crystal filters, we use those in the 185s, those nice tight little CR185 and CR187 receivers. And now we tend to really use quite a few of the surface acoustic wave filters in the IF sections. And if you want more technical details on that, you'll have to stop talking to the sales guy and talk to the engineer over there. And then we finally have the FM detector stage, and that's where that's our last bastion of defense on the interference side. I've got some key specifications, and I will make this PowerPoint available to anybody that wants it. You can either give me your email address, or I'll have a little stick. You can download it if you got a computer with you. If you don't, I'll just email it to you. So if you want to get a copy of this, but these are recommendations that we've had for years in our wireless applications guides, showing good ratings for sensitivity, AM rejection, and so when you're looking at specifications, you can kind of tell what the unit's really capable of doing, what's good and what isn't. It's great to look at specifications, but if you don't know what's what, it's a little hard to tell. Like they said, there's lies, there's damned lies, and there's specifications. So anyway, these are some recommended numbers to look for when you're looking at receiver and or transmitter specs. Another source of interference is intermodulation. Intermodulation is the interaction of the various radio frequencies that you're using simultaneously. You don't get intermod with one wireless microphone if you're in a really clean environment like the moon. You know, if you're just the only radio frequency, it's impossible to have intermod. Intermod occurs when you get multiple transmitters and multiple receivers up and running. For example, these two transmitters, if improperly coordinated, what happens is, here I've got body packs, okay? And this antenna is transmitting signal, right? But it's also receiving signal. Any piece of wire that's extended out there into the real world and gets it where RF can hit it becomes an antenna for incoming. So if this transmitter is close to this transmitter, the signal it can generate can go into this antenna and go right back down inside the can and talk to what's going on inside, become part of the party. And intermodulation is basically the interaction between these carriers. And it's a combining of the frequencies. Basic intermodulation, up here you can see an example. We've got a 650 megahertz and a 670 megahertz signal going into a nonlinear device, which is basically almost anything electronic nowadays. And it's going to yield these signals because they are additive and subtractive from each other. So 670 minus 650 is going to yield a 20 megahertz signal. It's exactly what we're doing inside the can to inside the receiver to mix down, get back to audio signals. We mix it with another signal and then get the subtractive product out. And then you've got your primary fundamentals, and then you've got the addition of the two, 650 plus 670. There's going to be a 1.3 megahertz signal generated as well. And that's just with two channels. But as you see, this is pretty far away from this one, and the 20 megahertz is obviously far away, so there's really no interference issue going on there. So that's basically, you can also get third order intermods where basically you've got the 650 has a fundamental, has a harmonic at 1300. So the 1300 minus 670 equals 630. And the 1340 minus 650 gives you 690. So you pick up a couple more frequencies there. And we're still just dealing with two transmitters. So if you put the whole mess together, this is the resultant list of what you can get just from a couple of transmitters working at the same time. That's just two signals. So when your director comes up to you and says, I want to mic everybody on the set, all the extras, everybody, you can just take this up exponentially, because as you add more channels, it adds up. That's why the frequency coordination gets so bizarre. So basically, you get even spacing and perfect third-order intermods if you evenly space out your signals. This is a big no-no. When you're doing frequencies, you know, you're on site and you just got to wing it and start putting in frequencies. Don't yield to the temptation to evenly space them. This is the thing that will get you, because if you look at 650, 670, and 690, they're all 20 megahertz apart. But 670 times 2 is 1340, and 1340 minus the 690 is going to interfere directly with your 650 megahertz transmitter. This is why it takes a computer to do a frequency coordination. Large-scale systems, 20 channels plus, can have thousands of intermod calculations, and it can really get in your hair. Now, there's some things that can make a difference here. Design is one of them. Transmitter design. An RF circulator on the output stage makes a big difference. It's a little component that's kind of cool. Larry could get into the engineering aspects of it. But basically what it is it's a small, very tiny circuit board with a small magnet located on top of it. And the magnet is charged to a specific field strength. The physics behind it is very complicated. The actual mechanical device itself is simple. But it's probably the priciest component in the transmitter, but it basically blocks RF signals that are coming down the antenna and trying to get into the unit. It'll take that incoming signal to ground. And in fact, the only thing coming out the antenna is the primary transmission. The circular isolator output will just basically prevent signal coming in, mixing up with the inside, and then coming back out with an intermod product. So it's a very effective method to help reduce that problem. And it's a design factor that also eliminates the other problem that you run into that you've been hearing about. This is one of the great legends in wireless, that the lower the power of the transmitter, the less you'll have intermod products. Intermod products are always X amount of decibels below your transmitted power. If your transmitted power is, say, 10 milliwatts, and your intermod products are 40 dB down, well, they're 40 dB down. They're going to be 0.1 milliwatt. But they're still 40 decibels down. Now, if I raise the power of that transmitter to 100 milliwatts, guess what? The intermod products will still be 40 dB down. They'll still be not a part of the picture if your radio design is capable of handling that. That you do not have an increased intermod problem, all things being equal. Now, if you had a combined system where you had some 10 milliwatt stuff and some 100 milliwatt stuff, yes, the 100 milliwatt stuff could possibly generate some intermod that would affect the 10 milliwatt. But if all things are equal, if you had all 100 milliwatt systems, you could run as many channels at 100 milliwatts as you can at 10.
A couple things here. Gordon did mention that there was frequency hopping and direct sequence. They're two totally different techniques. Frequency hopping is obvious, so you just jump around. Direct sequence, you actually take the carrier and mix it with a digital stream that is a series of ones of zeros, and when you mix that with this random noise, you actually spread the signal out. It's done very, very quickly. And we're doing that in this 4-channel link. And Gordon mentioned that we'd had problems with range and multipath and what have you back when we were doing the 700. With this other system, we are able to transmit over a 2 to 4 megahertz bandwidth, okay? Instead of transmitting in a 200 kilohertz bandwidth like we do with our digital hybrid, we're transmitting between 2 and 4 megacycles, depending on whether you're running 2-channel or 4-channel on the thing, okay? We are getting very good range out of it, and we've overcome the multipath problem by going to this wide bandwidth. But this is up in the 902, 928 band, so this is not going to bother any of the wireless microphone operations. The interesting thing about the spread spectrum, even though it has an AM component, it is spread so fast that this AM component is extremely supersonic, and you don't pick it up in the microphones. It's far, far out of the audio range. Our 700 stuff doesn't have a lot of AM component. It's got a small amount. We have gotten a little bit of AM buzz with some microphones with, in fact, one of our own, the M150, with the 700. But there's another wireless system that sends more information per symbol that's going out. And it uses 16-bit QAM, and it has a higher AM component, which causes more problems with various microphones. Fortunately, the microphone manufacturers have responded to these problems, even though it took them a year or so, and they are bypassing the microphones much, much better. And that is not as much of a problem as it used to be. We've tested some of these microphones for some of the manufacturers, and we found that they've improved the microphones by 20 or 30 decibels. The COS 11, for instance, had a little bit of problem. Some microphones were worse than the other. This COS 11X that they had, we hit that thing with a heavily modulated signal, AM signal, and ran it through a power amplifier so we could wrap about a watt into the microphone, and it seemed impervious to it. A very definite improvement.
Antenna receiver placement, the closer the better. In my little Intermod demo that I was trying to do there, honestly, if we'd gotten one of those antennas just a bit closer, you know, about half the distance, we would have gotten a 6 decibel improvement on our signal strength, and probably my locking in of with the FM capture would have been rock solid. So again, it's all dependent on how far you are from your intended signal. So the temptation, I remember years ago I went on the set of, what was it? It was, that movie with the snotty kid. Oh gosh, can't remember the name of the film. But the thing that struck me was it was the heyday of it was the glory day of wireless, because the sound mixer was in Florida. It was hot, sunny day, and of course the sound mixer was with his cart underneath the only shade tree within about a mile of the set. And he was sitting back there nice and comfortable in the shade and just, you know, picking up the signal wirelessly, and quite happy with the circumstance because he was comfortable, everybody else was sweltering. And so that day may have gone away. You may need to get your antennas close, get your wireless closer. Now there's a couple of ways to go about that. You can move the antennas closer, but now you're going to be dealing with cable loss. You have to remember that the cable is going to pull down your signal, and long cable runs off an antenna are going to reduce your signal strength. But your signal to noise ratio against the interfering source is still going to remain the same. Another solution is to get the whole receiver close with the antenna and then use an audio cable to bring it back to the cart. Of course, you have less loss in audio frequencies over the long cable runs, but again, you're kind of losing the whole sense of wirelessness. But closer to the antenna, the better. So that means, get the umbrella for the cart so that you can get closer, and even if it's out in the sun. Power rules. Power rules. That's not as in powers have rules, but power is what rules. The hotter your signal, the more robust your wireless system is going to be against interfering sources. Lower power is not going to help you. You want to be able to bury an interfering source in the noise floor. So higher power definitely makes a difference. Of course, there's the trade-off. More power means shorter battery life. So the battery issues come up and get you. But 100 milliwatts is what we've kind of standardized on for most of our transmitters, and that works well in many, many circumstances and helps reduce some of the problems. But just like you've been clever about hiding microphones on sets and so on, hiding antennas might become a factor. You can make some slick little antennas that can get in close.
The SM is the guy that gets warm because it's so small. And basically we're discharging a AA battery in about 4.5 hours, and that power, some of it goes out the antenna, but not much. Most of it's still in that transmitter. I did an experiment of taking a transmitter, completely covering it with an insulating material except on one side, putting it up against my leg and checking to see what the temperature was between my leg and the SM. And the unit got up to about 104, 105 degrees. The FDA says that you can have that on a baby indefinitely because they have devices that measure the amount of oxygen that's in a baby's bloodstream, and they do that with a heated pad, okay, and some other stuff. And anyway, you can do that 104, actually you're allowed up to about 106 degrees indefinitely on a baby, okay? So the SM cannot burn somebody because it's in a pocket, okay? If it's insulated all the way around, it might get above 104, but if you're not touching it, then it doesn't make any difference, okay? What we do have is a small pad that you can put on the SM on the side that's facing up against somebody, okay? And it doesn't feel quite as warm that way. One of the things that happens with the transmitter that I've noticed, if you take a transmitter that's off, no battery in it, put it in your pocket, okay? And about an hour later, pull that transmitter out, it feels warm just from your body temperature. Your body temperature feels warm to you. So some of the heat that's in an SM is just the fact that it's at body temperature, and the SM actually only adds about 7 or 8 degrees to that, okay? There's not a heck of a lot we can do about it. But reducing the transmitter power is not going to do anything because that's not where the power is getting absorbed. It's in the DSP, the A to Ds, and all the supporting circuitry. So we're starting to get to the point, at the moment at least, where transmitters can't get a heck of a lot smaller without them getting a heck of a lot hotter, okay? And the foam that we send out with the SMs is a hypoallergenic foam, okay? And I don't remember what it's made of, but it's not supposed to cause any irritation or anything. And if you need some of that and don't have it, let us know. We'll throw some in an envelope and mail to you. It's not expensive enough for us to bill you for it, okay? So if you want some, just ask for it, and it's reusable. One thing I'd like to say about the antennas, and probably will break after that, if you've got interference, and as Gordon said, one of the ways to get around that interference is to get the antenna closer to the wireless microphones. Gordon mentioned that you'll lose some signal in the cable when you do that, okay? However, you are attenuating the interfering signal as well as the desired signal, okay? So it's not as bad as it seems. In other words, if you're having to operate in an area where you've got interfering frequencies, you could run a cable out that gave you 10 decibels of loss, and it probably would not make any difference whatsoever to your problem, okay? Because you're going to attenuate your desired signal 10 decibels, but you're also going to attenuate the interfering signal 10 decibels, and what the receiver really cares about is the signal-to-noise ratio between the desired signal and the interfering signal, okay? Now, when you get the antenna closer to the person, your signal level comes up. You lose some of that down the cable, but you lose your interfering signal also. So you've actually improved your signal-to-noise ratio. Okay, let me say it another way, just so we all understand it. Let's just say that you put the cable 3 times closer, or cut the distance to 1/3 between the receiver and the talent, okay? You now have a 10 decibel pickup in signal because you're 3 times closer, square root and all that. You've got 10 dB more signal, okay? You could have 10 dB of cable loss and you still would have improved your situation because your desired signal level is just what it was all along, but now you've knocked your noise down 10 decibels. So if you're in this noisy RF world of LA, adding cable onto an antenna is not necessarily a bad thing, okay? Your range is, you're going to cut your range down, but you didn't have much range to begin with. You don't have 1,000 feet of range in LA probably. I'm saying that you can get the antenna closer to the talent and not worry about cable loss because the cable loss is going to affect the desired signal and the interfering signal, and you've increased the desired signal, okay? So all in all, you've improved your signal-to-noise ratio. You're losing almost nothing of 10, 20, 30, 40, 50, 100 feet of audio cable, okay? Given that you've got a good mixer with a low impedance output, decent cable, and you've got our transmitter, let's say, okay? You're not going to lose any audio at 100 feet. It's not going to be bad at all. Height is always a good thing, okay? Typically because you've got bodies and people walking around and other objects. And getting an antenna up 6, 7, 8 feet above the ground is always the right thing to do, okay? Well, this guy standing up there, you know, he gets in the way of those antennas, but I'm standing to the side of him a little bit.
You have to
but no,
think
that's always a good thing to do.
Think like an RF system and review the human body as a large sack of salt water, because that's what we are to an RF signal. So if you can get the end, now don't go to an extreme. I was on a location one time. It was a stage. It was a set, and they had gone too far the other way and taken a dipole antenna and hung it above the lighting grid directly over the talent. And you need to understand that when you're looking at the pickup pattern for a dipole antenna, it's like a torus, it's a donut. And directly above and directly below are the null points. So here we had the talent with their wireless microphone directly underneath the antenna in the dead spot. And they were complaining about multiple dropouts and so on. Well, what we did is we simply lowered the antenna to 8 feet, which got it above the heads of all the people, and got it clear the sacks of salt water walking around, and dropped that, and then the signal got very reliable. There's a nice little dirty trick you can do on a in a location situation where you really need to get that antenna close, but maybe you need to hide it. You can make a dipole antenna out of a coax cable. You need a BNC at one end to go on the receiver itself. At the other end, string out the cable to the location it needs to go to. At the other end, strip the insulation off about the top 8 to 9 inches if you're in UHF, okay? Spread the core, spread the
Shield.
the shield, the braid around it, so you can get to the core and pull the core out so that you're holding it. Looks like a Y. You've got shield going down here and core going down here. Then fold the shield back against the body of the cable, put some shrink wrap on it or some gaffer's tape around it, and basically what you'll have is a small dipole antenna that is just as thin as the cable itself. And that can be more easily discreetly hidden and yet be quite close.
Yeah, we sell that product as A coax B and C and A coax SMA, which describes exactly what they are. We'd rather you made them. We provide them kind of as a service. We do have an FAQ on the site that says what kind of links you should do and how to make the thing. Basically, it's a quarter wavelength of bare wire sticking up or insulation covered wire, okay? Unshielded wire is what I should say, and a quarter wavelength of shield that's coming back down the cable. And they're real simple to make and they're very effective. You can put them on people for that matter. We had a guy that was doing surfing a documentary, and he was losing the signal every time the wave would curve over the guys on the surfboard, okay? And so to get a little additional range, we made up one of these things, and he mounted the antenna right at the shoulder. And the reason he got away with it is this is just a floppy wire, so when these guys went tumbling through the water and their heads would flop over against the wire would just simply bend. It wasn't a rigid antenna, but it just about tripled the range that he had. These waves would curve over and he could still get whatever sound there is inside a surf. Yeah, that was on the transmitter.
You could do it at
yes.
either end.
Yeah. Keep in mind, transmit antennas, receiver antennas are reciprocal. If you've got something that's got 7 decibels a gain for a receiver, it's got 7 decibels a gain for a transmitter.
I was in
Okay.
Isn't the actual cable length, especially on the transmitter, come into play?
No, it does not. You've got a 50 ohm point right there at that shield. It's the fact that you take that shield back over there that balances that thing, yeah. No, you can have any length cable to that. Cable length comes into play when you aren't going into a 50 ohm termination, because a 50 ohm cable terminated with 50 ohms looks infinitely long to the transmitter. It looks like 50 ohms. It's when you're terminated in something other than 50 ohms that cable length comes into play then.
Question is, what about the issue of using an omnidirectional antenna in a crowded RF environment?
You're always better off with a directional antenna, okay? Unless, of course, you've got a thing where people are all the way around the antenna. But if you're off to one side, you're always better off with a directional. One of the things you can do with a directional that you can't do with an omni, obviously, is you can turn the antenna so the back of it, or wherever the null is, faces the interference. And you can actually do more doing that sometimes than you can getting the antenna pointed exactly at the transmitter. You might be 40 degrees off the transmitter and lose a decibel or two of signal, but yet the rear of that antenna is facing your signal interference source and attenuate the signal by 10 decibels. And keep in mind, it's signal to noise ratio is what you're looking for here. So directional antennas with the rear end pointed towards interference can do a lot of good. Yeah, exactly. And the only way you can tell interference is look at the meter on the receiver and turn the antenna around and see when you null it out. Don't do that from one position instantly. Try that from multiple positions. You may be looking at standing waves, multipath, what have you. Oh yeah, transmitter off when you do that,
Good
absolutely.
point, Jim.
Question was about broadband VRMs. One of those things I hated to do was come up with a broadband venue system. I like narrowband. We used to make helical resonators that were works of art that were extremely narrow. I've hated the fact that we've widened things out over the years. We went ahead and did a broadband venue. However, we have filters available, passive filters, that you can plug in front of the venue, okay? So you can make a venue equivalent of 1 block wide. And we've got filters that are 1 block wide, it's like 24, 25, 26, or 2 blocks wide. If you're operating with modules at 21, block 21 and block 27, obviously that's not going to work for you. The amplifier in the venue is the same one that's used in the distribution amps, okay? It is a very high power, very high current, high intermod device. It's one of the plus 43 dBm third order intercept points. And that's because we don't do tracking in the front of the venue module. We can't because it doesn't know what the receiver frequencies are going to be. The problem with the broadband is every TV station that's out there comes into that front end amplifier. It's a very tough amplifier, but everything's coming into it, okay? If you get away with it, great. But you might have an odd interference or something weird come up that is due to intermod between all these various stations coming in. Yeah, I would like to sell just, you know, standard VRMs like we used to make them, but the wideband unit is handy for the rental houses particularly, okay? They don't have to worry about, is this a block 2122, a block 2223, a block 2324? They don't have to do that. They've got one unit that they can grab. And I don't mind it as much because we do have the passive filters you can put in front of them. Kind of solves my conscience a bit. It is a bigger challenge, yes. Right, absolutely. Absolutely. RF is always a compromise.
We did come up with a block change program. It allows you to do block changes on your current units. Now this applies basically to products we're currently manufacturing. So anything that's a 400 series, SM, and so on. And in some of the older legacy products, the 200 series and so on, if it's less than 5 years old, we'll arrange an exchange for you on it. But basically, we'll do an RF board replacement. We're going to gut your unit and put new guts in. And what that does is gets you up to date on the board, puts you into a block that is legal and below the 700 megahertz range. And some of the single board units, however, it's actually more cost effective for us to do an exchange type program where we just basically take back the 28 and give you a 25 or a 22 or whatever it is you want to go to, rather than to change the board because it's just a single board design. And it's just much more cost effective from a labor point of view on our end to just do an exchange on the unit. It's not cheap, but it's a whole lot cheaper than new units. Basically, if memory serves me correctly, on a UM400A, for example, the board exchange I think is $270. And on a UCR 411A, the RF board exchange is about 511, something like that. That's a number that sticks in my head. So no, it's not cheap, but you are getting back a unit with a new RF board and everything tuned up to spec like a new unit. The VRT would be an exchange because it's a single board thing, and I don't remember the numbers. But you can contact us, and our service department can give you the number right up front because it is a flat rate. We're not going to come back and say, well, you know, you got a scratch on your case. It's going to cost you $100 more. Yeah, it's a factory thing because when we get it back in, we're going to vet the thing completely. We literally disassemble, we put in the new board, we run it through QC, the RF techs take it into the screen room, tune it up, make sure it's right to factory spec, recan it, and get it back out. So it's definitely a more cost-effective path. In all fairness, you got to understand this recent ruling banning 700 megs came out just November 4th, was finalized. So everybody's kind of sitting down and analyzing this, and you know, give them some time. But I know that I've heard that you guys are working on something. So,
is this blockchain program in effect now?
yes, you can send stuff in now. Absolutely. And I got to say something for the dealers on this. We called our dealers about this program because this isn't a moneymaker, and we didn't put them into the loop on this, but we talked to them first. And for example, I called Steve at Location Sound and said, this is what we want to do. Do you have a problem with this? And the answer I got from Steve was no, absolutely not. It's the right thing. So basically the dealer is bowing out of the middle of this, not trying to take their, take a profit on it. The whole idea is to offer as cost-effective a solution as possible. So Location Sound has been really behind the program. So right now, it'd be like a standard repair, and our turnaround times vary depending on how many units have come in and what their current load, but it ranges typically from 4 or 5 days in-house to 8 days in-house. Now, if we get really hit, I know of one rental house that called me up and said they got 150 units above 700 meg they want to send in. Now, that could be a hit, and what we'll do in a case like that is, try to parse our resources so that you guys with 1, 2, 3, 4 are not held up for 4 weeks because someone sent in 150. We'll parse it so that we can get you as quick a turnaround. One thing that helps our service department a lot is if you are on a deadline, you know that you're going to start shooting January 15th and you need it back by January 15th, let them know this right up front, and boy, they will bend over backwards to get you back out on deadline. Question is, do we have any idea when the guys above 700 meg, the new owners, are going to start using it? And the answer to that is no one knows. Now, we do know that in some markets, and I've heard that here in LA, that someone has cranked up a test transmitter briefly and then took it right back down. That's kind of an interesting question because, first of all, they have to have a client base that's going to use that bandwidth. They've got to sell it. And who in the United States doesn't own a cell phone? Their customer base is not going to explode dramatically just because of this. So I don't know. It could stay wide open for years. It could get swamped immediately. We just don't know. They're not talking about what their plans are. That's the sad part about this recent ruling is, the physics was completely ignored. This was a political thing. The physics was completely ignored because if someone cranks up a megawatt transmitter or a 100 kilowatt transmitter, you're off the air. You're going to have to move your wireless. You're not going to interfere with them. It's the Doberman versus the Chihuahua. And you guys you would have to move. You would not be able to interfere with their signal. But that's the case they presented. We got to get all these illegal users out of our spectrum. Good question. Are lower blocks opening up? Fortunately, kind of coincidentally, there were some of the substrates used in the ceramic resonators we use in some of our products got changed, and one of the things that was keeping us out of lower blocks, 1920 and what we call 470, which starts at 470 and goes up to 496.5, is these ceramic resonators were too big to get into the transmitters at those lower frequencies, but the substrate has changed and now they can make them small enough, so we are able to offer blocks 19 and 20. And Larry's going to talk a little bit about those blocks after the lunch break here. A good question, and again, I'm going to admonish you slightly because you're using the term white space when talking about the digital dividend. Remember, they are two separate problems. White space is the utilization of the frequencies between 470 and 698 by unlicensed devices, like the routers I was talking about. The sell-off of spectrum is the digital dividend. And I guess the core of your question is, are they going to sell more spectrum? And the answer to that is, based on the current legislation, what was passed in the Balanced Budget Act in 1997, the answer is no. The only part of the spectrum that was up for sale was 700 to 806. None of the VHF channels have been touched, and everything below 698 is not up for sale. They're not going to empty it out. In fact, one of the good things, Larry will touch on this. I'm stealing some of your thunder now, Larry, but one of the things Larry is going to touch on, and it bears repeating, is that getting low-powered white space devices into that spectrum in the long run may be the best thing to happen to us, because if they don't use that spectrum, it will be, quote, continue to be unused, and the temptation may be there to sell it. If it gets occupied with other low-power use that's not going to be an issue for you on your sets, that will protect you in the long term. So that may be the silver lining. And like they said, every cloud has a silver lining, and 10,000 people a year get killed by lightning looking for it. So, great question. Do you have enough? If you guys all got your stuff licensed, will that give you some oomph? Yes, it would pay. Now, the question is, we're still waiting for this final clarification from the FCC on licensing for you. Now, you could license right now as a Part 74 user. My suggestion is there's not going to be any radical changes in the next year or so. I'd wait until they clarify that licensing process. They might make it better, simpler, easier, lower cost. And if they do, then absolutely. And we'll keep a thing up on our website about licensing. Because if you guys could really have some impact on that, yes. Instead of 900 licensed users, if we could get a few thousand up there, and with the names that are associated with it, would sure help. Now, something about 27, for those of you that have 27s, keep in mind you didn't lose all of 27. The first 6.1 megahertz are still perfectly legal to use. And after the transition, you may want to take a look at that and see, because that 6.1 megs may be just wide open, clean as a whistle, and certainly worthwhile staying in. You may not be able to use the upper part of it, but keep in mind that maybe not all your work is in the United States. And Block 27 in other countries may be allowed. That's another factor to consider, is flexibility too. So you're not illegal in 27, just part of it. The question is, if he licenses for a particular location, even though most of you are very mobile, in other words, as Larry pointed out earlier, it can be site specific. You're saying my antenna is in this location. Again, the FCC has not made a big effort here to go out and get all you guys, and find out where you are or anything, because you've been a non-problem. You're not a problem now, you're not going to be a problem coming up. But the advantage in licensing, and I would say license for wherever you call home, as a business. And if you operate out of your house, license at your house location. It's the visibility of the license, not where it really ends up getting used, because you're not going to cause trouble where you're going. Larry will tell you some interesting stuff about the requirements for the unlicensed stuff. It has to identify itself, so if it does cause problems, they can hunt it down. So actually, licensing just gives you visibility to the FCC. In Australia, they handle licensing. Wireless microphones in Australia are called a Class 2 device, and you're supposed to register, not license, register. You fill out a postcard, mail it in. And when they looked at their database, when they were considering the digital dividend in Sydney, they had 10,000 registered wireless microphones on their database. 10,000. As opposed to the 960 or 974 in the United States. The problem here is because we weren't visible, they were thinking this was unused spectrum. The comment here was, he thought there were some people, going and talking to Washington. And actually, there's been a coalition of wireless microphone manufacturers headed by Shure, who has been really fighting on behalf of wireless microphone users about this issue. And they have had a full-time lobbyist in D.C. They have had a bill introduced by the congressman in Illinois to protect wireless microphones. There's been a lot of pressure exerted by wireless manufacturers. Sennheiser's been in on this. We've been in on it. Everybody's been in there basically plugging away, banging Washington, saying, hey, wait a minute, you don't realize how ubiquitous this is. In fact, let's go have a hearing in the U.S. Senate about this, because you're going to be talking on Lectrosonics wireless microphone in that hearing. There's been a very strong effort in Washington to make people aware of the issues. And I think when you hear what Larry has to say about this rule, you're going to realize there's been some effective lobbying done, because the new ruling is pretty tough, and it's not on us. So that's going to be the good news part coming this afternoon. Well, yeah, we were much more visible than the 974 in the database, but that's the number that Google and Microsoft and all the other guys have been leaning on. Look, only 974 legal users, insignificant compared to the millions of Americans that'll benefit from having, Wi-Fi on steroids. And so that's the number that can be proven. Everything else is conjecture. So the point brought up here about antennas on our shark fin style antenna is the pickup pattern is narrower on the vertical axis and actually relatively wide on the side-to-side axis. And like Larry was talking about, the null point is directly behind. So if you've got let's say we've got John on a wireless microphone here. I could point the antenna directly at him, but if my interference source is right over here, I'll be better off pointing off a little bit this way, putting the interference source behind the shark fin, because John will still be in my pickup pattern. He'll be down a decibel or two, but they'll be down 15, 20 dB. So you can get a big improvement even with an off-axis pickup. And there's also no reason in the world that you have to have identical antennas on a diversity system. You can have a shark fin on one side and an omnidirectional on the other side to handle the shot where they're coming in on the horse and then riding past. So you got a good pickup coming in from that side and good pickup as they pass by.
In this part, we're going to discuss some of my favorite subjects, which is government regulations and federal documents. They have an important bearing on your life, as I think you've seen. We're going to talk about the good, the bad, and the ugly of this recent ruling. And we're going to do them in reverse order because there's a lot more good than there is bad and ugly, in my opinion. The specific document is this FCC, the number's not up there, FCC 08-620. There it is, right there at the very top. And you can Google that, and you go right to the PDF in one of the government printing offices if you want to read all of this. And it's 130 pages of rip-roaring fun, a twisted plot, and an absolutely no surprise ending, okay? The ugly thing is that wireless microphone users are not sure of what's going to go on, okay? Unfortunately, either are the microphone manufacturers. We think we know, but we're not positive. And the bad thing is also that, or the ugly thing is also that they may change all this in a couple years. Basically, what this white space document and what have is it's a trial run. They put forth some regulations, put some requirements on the white space device people, and they're going to see if this works out over the next couple years. At that time, they'll review it again, and they may make some changes, and my guess is they probably will. The good thing here, as Gordon mentioned, is a lot of the analog stations are going to go off the air below 700 megs, okay? Because right now you're running analog and digital. The analog is going to leave. That's going to open up some space for you, okay? The white space devices are going to be operating in that remaining spectrum. So you wonder, well, what's actually good about that? And the good thing is that the FCC has put some extremely tough requirements on these WSDs, white space devices, okay? And the white space devices are so tough that I would hate to be on the other side trying to make a white space device work, okay? Now, of course, they've got a few $1 billion more than we do, but still, I think it's going to be a really tough job. The FCC did discuss wireless microphones in this document, and that's page 54. You got it? Okay, page 54, paragraph 151, right down here. One of our considerations in this matter is to ensure that the channels remain available for use by wireless microphones. They came out and said that, okay? That those channels remain available for wireless microphones. While we are aware that many wireless microphones are now operated without the required license, we nonetheless understand the important function that wireless microphones serve and find that it is in the public interest to preserve spectrum in the TV bands that is available for their use. As far as I know, that's the first time they've ever said anything positive about wireless microphones or even recognized that they exist, other than some rules and regulations, okay? They've come out and said that these things are in the public interest, and certainly they are. Part of this is because of Shure and the other manufacturers that bent their ears and talked to them about all the things that wireless microphones are doing, okay? Further down in this 130-page document, you've got what each commissioner thought about these white space devices and their impact on these channels, okay? Just about all of them mention wireless microphones, where they're used, and why they're important, okay? I just think that's a really good thing. The technical requirements on the WSDs, and that's on page 98. Page 98, it'll take Gordon a little bit to get there. Here we go. Subpart H, television band devices. Note that it's page 98. That's where the real meat of this document begins, okay? Because here is where they're saying these are the technical specifications these white space devices are going to have to meet. This is the part that they're going to put into the rules and regulations. The rest of this document is basically discussion. Here's what people told us. Here's what we think. Here's what we're going to do. They repeat the same thing over and over. This is the real meat of it, if you call this document up and read it, okay, from page 98. There's 4 power levels for these white space devices. The fixed devices can run 1 watt. Now that's a fair amount of power, okay? And that actually could do some damage. This is only allowed in fixed devices. They are allowed to have a moderately directional antenna to where their effective radiated power is 4 watts, which again is a fair amount of power, and that'll go some distance. However, the things that these fixed devices can do are fairly limited. Fixed devices can talk from one fixed device to another. In other words, like a backhaul thing where they'll be sending data back and forth between 2 points that are located about a mile or so apart. The FCC feels that these fixed devices will not interfere with TV stations, wireless microphones, and the rest of it because there's not going to be that many of them. The next device down is 100 milliwatts. This is for portable devices. And this is devices somebody would carry along, like an iPod that is set up to receive TV broadcasts, okay? Or video data or something of the sort. Those can have 100 milliwatts. If they operate adjacent to a TV channel, they're only allowed 50 milliwatts, okay? Or I'm sorry, 40 milliwatts. If they're a RF sensing unit only, they're allowed 50 milliwatts. Now here's what an RF sensing only unit is. All of these devices, the fixed device, the portable devices, all of them are required to have spectrum sensing. And basically, when they are turned on, they have to listen for 30 seconds to see if they can find any kind of signal in a 6 meg spectrum that is a wireless microphone, low power TV transmitter, or a TV station, okay? If any of those things occur in that 6 meg channel, they can't come on in that channel. You can have one wireless microphone at the edge of a 6 meg TV channel. If they pick it up, they can't use any of that channel. They can't use any of that TV channel at all, okay? They have to be capable of detecting at a minus 114 dBm, okay? This is way down in the mud. This is about 0.4 of a microvolt. Most wireless microphones squelch at about 1 microvolt, which is 107 dBm. This is 7 decibels below that. And this is getting down close to the noise floor. And they have to sweep or somehow detect in that 6 meg channel, find a wireless microphone within 30 seconds and detect it. For a TV station, they detect in a 6 meg bandwidth. For wireless microphones, they detect in a 200 kilohertz bandwidth, which is the same bandwidth that we use, okay? So basically, they have to find a signal at the same level or a little lower than what most good quality wireless microphone receivers will detect a signal, period, okay? So this is pretty far down. In addition to having to do that, all of these devices, with some exceptions, all of these devices have to have a geolocation capability. This means they have to have some undefined way of determining where they are within 50 meters, okay? It can be GPS, which is one of the things that's mentioned, satellites. That'd be kind of expensive to put that chip into a device, but it can be done. It could probably be triangulation like they do with some of the cell tower cell phones and what have you, but they have to determine their location within 50 meters. Once they've determined their location, they're required to go out and look at a database. That database has a list of all the TV stations that are in the area, low power TV translators, what have you, and licensed microphones, licensed wireless microphones, which says that a studio could get licensed, okay, and list the frequencies that they're going to use, at what times they're going to use them, and what have you. And this white space device has to go onto the internet, look all that information up, and then not operate on any of those frequencies. And if you say that you're in the middle of a 6 meg TV channel, it cannot come up on that 6 meg channel. Okay, that's in addition to the sensing that they have to do. The only exceptions are the fixed units, and that's because on the fixed units you can program the longitude and latitude into it and tell it exactly where it is. Okay? There is a client unit that doesn't have to have that, but the client unit talks back to the master unit, the fixed unit, and that unit tells the client where it is. Okay? So the geolocation capability has to be in every one of these white space devices. That's where the spectrum sensing, that's where the spectrum sensing comes in, okay? Is basically it looks to see if it can find a clear channel, okay? But if it connects, the first thing it has to do is look and see that there's nothing else in the area. If it finds that there's nothing on that channel, it doesn't have to connect again for 2 days. It can continue to operate. Basically, at 11:59 midnight of the previous day, if they can't make a connection in that time, they can operate for another 24 hours, then they have to shut down. So you're right, this is kind of a catch-22. How can they come up? However, what they can do is listen, okay? Try to connect to the internet by listening, okay? Yeah, but you know, what are they going to listen to? Some device that supposedly is already hooked up and running legally. Basically, it's a chicken and egg. Where do you get the first units, you know? But that's one of those little fuzzy things that they figure will just kind of go away. Okay? The other thing that's really a kicker here, in my opinion, is that the power that they have, this 100 milliwatts and 50 milliwatts and what have you, is conducted power from the device to the antenna. But the antenna is defined as a 0 dBi intrinsic device, okay? And if the antenna has any gain whatsoever, they have to reduce the power by that much. Every kind of antenna has gain. A vertical dipole or a vertical quarter wave whip, okay, is pretty much like a dipole. It's got a gain of about 2.7 decibels. A dipole has 2.7 decibels. Our transmitters, okay, this is one leg of the dipole, the body is the other leg. This transmitter has a gain of about 3 decibels, okay? If they put 100 milliwatts in this kind of device, they'd have to run the output stage at 50 milliwatts because they have a gain antenna. So this 100 milliwatts we're talking about here is not the same 100 milliwatts that we've got in an electrotransmitter. It's actually 2.7 decibels less than that, best case. Absolutely best case. So what you're really talking about here is a maximum of 50 milliwatts for the high-powered units and about 20 milliwatts for the lower-powered stuff, okay? That's one of those things that, wow, this is kind of neat, you know. These guys have got to cut their power down. Now, if they've got an inefficiency, if they've got an antenna that has less than that amount of gain, okay, then they can run the full 100 milliwatts into the thing. However, they can't turn it up anymore. If they've got an antenna that is slightly lossy, they could get away with 100 milliwatts, but we don't care. It doesn't get out into the air, okay?
Why would a mass manufacturer even look at this if there's so few channels available?
They feel that there are so few wireless microphones out there that this won't be a problem, okay? I don't think they realize that, you know, well, if you're a mile away from a wireless microphone, you're not going to pick it up at all. You're not going to see it, not going to detect it. And so you could operate one of these devices. There, probably 99.9% of the country is more than a mile away from a wireless microphone at some time, okay? Keep in mind, they can operate on this channel for 5 or 10 minutes and switch over to another one. So they can find a place to operate, yes. Okay, That's why I was talking about things are pretty good right now. They're going to reopen this in about 2 years, and it's 2 years from the November 5th or whatever the date is on this report. So November, a couple years from now, they're going to go back and look at this and see if the spectrum sensing, the geolocation, and all the rest of this stuff is working out, okay? And if it works out, they'll leave it alone. If the white space guys say, come on, we can't live with this, and the wireless mic people are saying, well, we're not having any problems, they'll probably allow them to go a little more power or change the rules some. No, the database does not exist, and again, it's one of those things that they're going to create somehow. They're talking about some private companies putting this database together, and they put some restrictions on it. All the databases have to come back with the same information. No matter which database you go to, you're going to have to get the same information. Google wants to do Android phones, okay? And their little picocell things where this phone talks to that phone, talks to the phone down the way, and they can run low power, but yet they transfer the signal until they get back to a tower or something of the sort. Google's got many billions of dollars. They'd put a database together like this out of their stamp money, okay? And maintain it, because that would allow them to do this other. Somebody's going to have to put that database together before they can do these devices, but the people that are behind this are big. They've got the money. Intel's another one, for instance. It's a mess. I've looked at the document that they have, and I get about 3/4 of the way through it and give up in disgust, okay? It can be done. People have done it. I'm sure some of the broadcast people would know. What I'd like to see is the broadcast people have to do it anyway. I'd like to see some of the studios get their wireless in there, because they're at a fixed location. They very definitely are in movie production, okay? Keep in mind, the only reason that wireless microphones are allowed to operate under Part 74 is to produce movies and video material and what have you for television stations and radio stations. This is a broadcast thing. We are operating not for the movie industry, but for the broadcast industry, okay? And it's that the movie industry makes product for the broadcast industry. But given all of that, studios that do that all the time, okay, could get licensed. And there's a lot of licenses out there. How to do it, I don't know. I would try saying, we're at this location, I want to license this frequency and do a different frequency for every wireless microphone. You know, the setup that they have right now is not suitable. I mean, the form setup is not suitable for wireless microphones. I'm sure some people are going to be addressing that and trying to get the FCC to change things. Keep in mind, the FCC does not want to deal with this. They never have wanted to deal with wireless microphones. They've ignored them now forever. Okay, 943 licenses. They know there's 10 million people out there using those things. There's 943 bar bands in LA, I guarantee you, and every one of them is using 6 to 10 wireless microphones. So the FCC has just had benign neglect for this whole issue, okay? It only came up because of the white spaces. But on the other hand, the FCC is trying to protect wireless microphones. See, it's not that you're being legal. That's not the important thing here. God, did I just say that? It's not that you're being legal, it's that you're getting a license. It's that you're getting a license in front of the FCC, okay? License a single unit at a single location. The purpose is not to make you legal. The purpose is to get the license in front of the FCC. And the defense always is, we had interference, we had to change frequencies. They're not going to bother you about it. If Warner Brothers, for instance, okay, registers a bunch of frequencies on their lot, they can't operate any white space devices within 1 kilometer of the center of that lot, or where the transmitters are. Now, if you got a huge lot, incidentally, they'll let you give different coordinates for the different places in the lot. So, I mean, you could take the 4 corners of the lot, and now you got to stay a kilometer away from that, okay? They cannot operate there because every one of these devices has to check the internet, the database, okay? The only reason I mention the studios is they're one fixed location, they've got lawyers, and they very definitely are making movies for television production. Sound mixers might be doing other things, okay? But yeah, I mean, if we could get sound mixers to do it, that'd be great. What I'd like to see is the FCC come up with a shortened form that a human being can understand and get this stuff filled out, you know. It's not going to hurt anything to make wireless microphones legal. they're going to operate either way. At least it would show them that it's a responsible community and there's a lot of us out there, you know? Okay. Okay, I mentioned the sensing. I think I covered this. The unit comes up, looks for 30 seconds to see if there's a wireless microphone. If there is a wireless microphone, it has to vacate that channel. Also, if the white space device is operating at least once a minute, it has to basically shut down and look to see if there's a wireless microphone or something else that has come up on that frequency. If it detects something inside that minute, it has to shut down within 2 seconds. On average, that says when you flip your transmitter on, if there's a white space device on that frequency, it's going to shut down on an average of 30 seconds. Okay, again, that's fairly onerous all in all. They have to stop and start their data transfer every minute. And they have to go out there and look for wireless microphones and what have you, low power devices at this minus 114 dBm. The other thing here, page 90, Gordon. Oh, great, gosh, you're good. This guy right here, certification by telecommunications certification bodies. Those are TCBs. The FCC is a very underfunded organization, okay? Anytime there's a budget cut, they get cut. 10 years ago, they couldn't test all the satellites that were going up in space, okay? There was nothing they could do. They depended upon equipment from the satellite manufacturers to test the equipment because they couldn't buy it, okay? If you talk to the people at the FCC, you'll find, and I hate to say this, you'll find some pretty inexperienced people, okay? Because they can't simply pay to get the kind of talent they need there, okay? They are underfunded. They are handling one of the most important things in society, okay? Communication. I mean, these guys handle the telephones, the whole thing, okay? Any kind of communications, and yet they are grossly underfunded. So they set up these certification bodies, okay? So that a manufacturer like Lectrosonics no longer sends the wireless transmitter to the FCC for them to check out. We send it to one of these TCBs, or at least the results of all the testing to one of these TCBs. The TCB signs off on it according to the rules and what have you, sends that on to the FCC with a big OK stamp on it, and we get our certificate so we can sell that product, okay? However, on the white space devices, the FCC said, we're not going to do that. We don't feel that these devices are going to work. And therefore, we want to test them ourselves. We don't want them going off to an independent body. Because the fact is, the various devices that they've tried to use to prove that this spectrum sensing would work, in my opinion, failed miserably, okay? A couple of the devices, even in the last run, would not detect wireless microphones. They tried it at a large stadium, and they did not do a good job at all. If they try to detect a wireless microphone next to a TV station adjacent to it, the TV station so badly overloaded these devices that they said that this TV channel is full, even though there was nothing on it. In other words, the bleed over from the active TV channel bled into the adjacent channel so that this white space device said 100% positive. There's devices here, and there weren't. Now that won't work. They can't do that. So anyway, since these results were pretty mixed, but the FCC wanted to do something, they said, we're going to test the units here to prove that they do operate, okay? And that's this guy right here. Okay, both the Consumer Electronics Association and SURE support this proposal, and no parties opposed it. Of course they didn't oppose it. These are the tough guys that are going to check this stuff out, okay? So that's another important thing. As far as frequencies go, the white space devices cannot operate below 512 megs, okay? That's our block 20, which says they cannot operate in our block 470, 18, or 19. They start at block 20, okay? And the reason for that is there are other sales of that, other users of that spectrum, okay? Part 90 and part 20 that are operating between 470 and 512 in 13 markets in the United States, one of which is LA. But it doesn't make any difference. Nowhere in the country can a white space device operate below 512, with one exception. They also obviously can't operate on TV channel 37 because that's the astronomical frequency, okay? In areas like LA, well, in the United States, the FCC feels that this, it'd be 42 megacycles between 470 and 512 is enough room for the wireless microphones to operate. In other words, white space devices cannot operate there. You'll have some TV stations, but not as many as you used to. So they feel that's one place that wireless microphones can go. If you're in an area like LA where there's other users of that spectrum between 470 and 512, then they're going to set aside 2 channels on either side of TV channel 37 and prohibit white space devices from operating on those frequencies in an area like LA, which would be channel 36 and channel 38. Okay, white space devices won't be able to operate there. If there's already TV stations there, then they'll go one more over. They'll go over to channel 34 or channel 39, one or the other, until they get 2 channels as close to TV channel 37 as they can. But the white space devices won't be allowed to use there. The FCC feels that wireless microphone users can operate in that area. The problem is these things are so far apart that if you buy, block 19 and it won't operate in LA, you can't switch up to the 2 available channels that are around TV channel 37. Okay, but still, it's another regulation put on these poor guys. Okay, any questions? That's about all I had to say about it. I don't think the white space thing is going to impact wireless microphones much at all. Okay, this spectrum sensing thing is just huge. And there's very few technical things put on the white space devices. Their emissions have to be 55 decibels down in the adjacent channel to the one they're operating in, but they haven't said anything about modulation at all. They can use any kind of modulation. They can also use bandwidths greater than 6 megacycles. If they can find 2 TV channels unoccupied close to each other, they can operate 12 megs wide. So they've left it pretty far open. These are initial rules. They'll refine them as time goes along. But right now, like I say, I think they're pretty tough.
Yeah, is there anything on the technology horizon that would allow frequency agile units to span hundreds of megahertz?
Not in Part 74. Okay. Yeah, okay. The FCC's not allowing anything like spread spectrum in there that might dodge some of these issues, okay, or might be able to interoperate with other stuff. Yeah.
I was thinking of a standard FM that you could simply tune over that wide a band on a single channel instead of being limited to 25 megahertz or whatever the ranges are.
Some other people are going a little wider than that now. There are some technical reasons that make it a little tough. Output filters, front-end filters on the receiver, it just goes on and on. You can build a lousy receiver that is 100 megs wide. It's kind of hard to build one that's got pretty sharp filtering, but obviously people are going to be driven to that more and more.
If wireless mics are exempt from the white space device requirements, is anybody thinking along the lines of creating a wireless mic that operates under the white space device requirements? In other words, that's
It could certainly be done, absolutely, okay? The problem is you have to shut off. You have to shut off every minute, check, see what's out there, scan the doggone thing and say, hey, I'm going to come back on. That's going to introduce a fair amount of delay, okay? That's the problem. They do say that you can use a remote antenna, okay, to detect this so that you could keep your white space device on and listen on the remote antenna. However, that's got to be really hard to do, to have a remote antenna that's not going to pick up the white space device, but you can try it if you want to. I think that thing's kind of impossible. Our rule of thumb was when we went from VHF to UHF is that you about tripled the range because your antenna efficiencies went up and diversity worked real well. But even with a single antenna system, you get about 3 times the range at UHF that you do at VHF. And we had some darn fine VH receivers. Those were very, very sensitive units. Helical resonators up front, crystal filters, the whole 9 yards. They're about as good as you could do it. There's no reason that you can't get perfectly good sound at VHF. You're allowed the same kind of deviation. You're only allowed 50 milliwatts, but you can have the same deviation, you've got the same channels and what have you available. But the problem is antennas. Now, for people on a cart where they can put the antennas a fair amount of distance and they don't care if they're 20 inches long, VHF would probably work out just fine, okay? And yeah, I mean, diversity works just as well at VHF as it does at UHF. The dropouts are slower. As you walk along, you'll have a dropout, let's say, every 5 feet, where you might have it every 1.5 feet with UHF if you're getting severe reflections, you know, right on the fringe. The other problem with VHF is the transmitter antenna. It needs to be long, and the problem is it couples into the body heavily, and you actually radiate very little power into the mic cable. And the reason we built it into the mic cable originally is we found out that was no worse than the dangling wire antenna. It wasn't that it was a good solution, it was that it was only as bad as the dangling wire, okay? Yeah, a scanner will not give you any direction because basically it's just a 50 ohm device that you plug an antenna in. You'd have to have a directional antenna, or multiple antennas that you could point electrically, let's say, you know. But I mean, you can make a directional scanner just by taking an antenna and rotating it as you look at the screen. We had a program that was just outstanding. The problem was it found so many hits it took a real expert to understand it. And basically, we would just simply have customers call us. The people at what is it, Professional? Right there we go, right there. Yeah. That's their IAS system. And what is it, Professional Wireless, PWS?
Yeah, Professional Wireless, and if you go to, I think it's professionalwireless.com/IAS, or just Google IAS frequency, you can download this software, run it on a 15-day trial. It runs about $250 for what they call the non-professional use, which will do up to 30 channels, or you can get the professional version, which I think is about 400. That will let you do almost any number of channels. This is the software we currently use, and it's very effective. What you see down at the bottom of the graph there is LA as of now. And it goes out and onto the web and references the FCC website and pulls down the latest information automatically. So when you log on, you can have it go out and check if you're tied into the internet, and if you're not, it'll take your last download. So this band right down here is showing you the current LA situation, and these are the DTV broadcasts, and these are the analog broadcasts, and then it's very simple to run a coordination. You can pull up the brand and the block number, and it's got all the brands, all the blocks, in all the key professional stuff. And you can go up there and you can say, well, let's pull up Lectrosonics block 470, for example, and then run test. All right, let's try that again. Now, if I pay attention, there we go. Now let's run it.
I saw that Mac computer.
There we go. See, there's 22. Basically, you just call up. Those are all pre-coordinated, yes. 300 megahertz of power? Sure, kilohertz. That's what I meant. Yes, oh, absolutely. That'll work just fine. We did a concert in a theater where we had 18 wireless, we had in-ear monitors, we had comms, we did the whole package down in San Diego, and the theater owner told us, we've never been able to get wireless running down here. We've been told by the manufacturers, forget it, you're doomed. And we got all the channels, a total of 26 up and running, and ran 5 concerts without a single hit. In fact, at one glorious moment in my life, a hardwired mic went down and we saved the day with the wireless. So. But this software is, this is what we use. And another thing, if you're on the road, you're out there on site, You can call us on our toll-free number, longitude and latitude or zip code, any of those, and what we'll do is we can run a coordination for you based on what you have and get answers to you generally while you're on the phone. Unless it's a massive job. When it's something like Survivor, when they call up and say we need 84 channels, we need a day for that. But it'll do it.
You know, let me say this, that for $250, this is a buy.
It is.
You got $10,000 worth of wireless equipment out there. This $250 is well worth it. And even though that may seem expensive for software, these guys support this and they keep updating all of this stuff, okay? And that's what was killing us, is doing all the updating. Also, it takes in the front end bandwidth and IF bandwidths and what have you. So it is designed for each one of the different brands. Yes?
It's called
IAS. Yeah, and it's sold by Professional Wireless, which is, what, a division of Gotham?
Division of Professional Wireless Mask Sound.
Mass Sound, okay, right.
I think it is Windows only. Sorry, guys.
Is that 250 one time or is that annual?
That's one time. That's one time. I don't know if they've got upgrade fees or what have you, but again, they support the product. We've been using it because we were spending lots and lots of time supporting the program we had and trying to get information from the FCC website as to what stations were up, down, or sideways was really tough to do. We've always been running fairly high-powered transmitters, okay? And that is one really good way to get past the problem. I mean, if there's signal on the frequency of the receiver, you've got a problem. And if you've got signal absolutely everywhere, there's not much you can do. A higher powered transmitter will overcome that interference, okay? And we've been doing 100 milliwatts now for, I don't know, 10, 15 years. Also, we've got the quarter watt, okay, which is another way of getting up above this interference. There's not a heck of a lot that can be done. Again, if somebody's on your frequency, it's not much you can do about it. We did come in with the block 470, 18, 19, and 20, you know, to extend the frequency range down there to make up for losing everything above 700. We are looking at some other frequency bands, but there's not any that are really good. After all, these people that are in the other frequency bands are trying to come down here. There's a reason for that. This is good frequencies. And so us trying to go up and operate over in the other bands, like, you know, 2.5 gigs, it's not going to work very well. You know, we are making this 4-channel digital link, and it's running at 902 to 928.
You may have seen in the back, too, for those of you that are doing bag systems with repeaters back to the cameras, a camera hop, we have got in the works, he's holding it up back there, a 4-channel single frequency. It's a single carrier that carries 4 tracks of audio back to a single receiver that breaks it out into 4 tracks of audio. And that's up in the 902 to a 928 band. And it's a different type of platform. It's digital. That's going to resolve part of the issue because you'll be able to, if you're doing hops, you're doing repeat where you need repeat of multiple channels to a single receiving location. That narrows it down to a single frequency outside your bandwidth for your wireless that can go back to the cameras.
And let me say another thing here. You're asking the question, what is it we're going to do about all these problems and what have you? The fact of the matter is the problems started over a year ago, okay, when they had to run digital and analog. That's disappearing. The analog part of that's going away, okay? So it's going to get better, I hope to God, on February 18th.
Well, yeah, for a while it'll get better, and then do something really.
Well, we don't know that it'll get that.
I don't know that that's going to happen. Broadcast stations are not making money as I read the news. Yeah. I mean, you're getting more and more cable, you're getting internet, you're getting all these other methods for people to, you know, I don't know how many more broadcast stations are going to get built.
Let's put it in perspective. This is not really that much different than the bar bands out there with tons and tons of wireless. Believe me, there's a lot more of them than there are of you. Yet how many times have you really been blown off the air by a bar band?
Also, after the digital transition, people will discover how bad ATSC is, and we mean just chuck run.
You know, what is it? 10% of the people now get over the air, and the rest of it is cable or satellite or something of the sort. You know, I'm praying the broadcast stations will stay around, because let me tell you what, when the broadcast stations are gone, so is the spectrum. That's the only reason that wireless microphones can operate is because of broadcast TV. So I'm praying that they hang in there and you know, do quite well.
So we lost our 700 megahertz privileges because the broadcasters lost it.
Well, yeah, but the
Yeah.
thing was, they had this tremendous amount of spectrum, and they were only using about every 5 channels was what they were using in most areas, and they were not using the stuff above 700 much anyway, other than in markets like this, because you get less radiated power for every kilowatt you burn, okay? And then on top of that, you can't go as far because the path length is measured in wavelength. So low frequency stuff like 470 would go just about twice as far as stuff that was up above 800. What was the top of the old 800? It was 880 or 8?
Channel 83.
Yeah, channel 83. Those things were well above 802, you know. Nobody wanted it because they wouldn't operate from TV channel 69 up to channel 83, so that disappeared. And then people weren't using the stuff around 69, so now we've lost everything down to 700. So no, we need to keep those broadcast stations alive, absolutely. And you know, some of this white space stuff might not be too bad.
It sounds like in your summary of the white space that you don't expect too much of it to actually be realized.
Boy, it's tough. I think they can do it. I don't think it's going to be a problem for wireless microphones. That's the thing. Look, if you're inside your own house, okay, and you got a router up there at 500 megs and there's nobody else operating around, and you've got this little 10 milliwatt device on your belt that's communicating with your router back and forth and works perfectly, a wireless microphone's probably not going to bother you in your house because they're off at a bar band somewhere miles down the street. There's nobody next door to you, so it's going to work just fine.
Well, maybe not these houses.
Well, okay, yeah.
The assessment that the white space devices are not going to be a problem is based on the present regulation.
Absolutely, and
Politically, all of those turn over, and the white space device people are all of a sudden.
absolutely. That's why I have said that twice, and now the third time, reminded by Jeff, is this could all change in 2 years. That's when they're going to look at this again. And they may put out different rules and what have you for the white space devices. But at least they have said that wireless microphones are good things and they're in the public interest, okay? At least they've done that now. And I think a diplomatic letter that says we're concerned about what's happening with this, keep us in mind. You know, we're an important part of the economy, etc. You know, that.
Yeah, petition, and also to your congressmen, your senators, you know, be visible. The licensing makes you visible. Letters to your congressman makes you visible. But one letter from a group to a congressman is one letter. 600 letters to a congressman is a whole different animal.
They need to be
Remember that.
individually written because
They need to be
you know
visible.
you get this petition that's signed by 10,000 people. It doesn't count that much. You know, 10,000 letters, however, 1,000 letters. Yeah, that helps too. Okay, we're about 7 after, Gordon.
Yep.
Okay.
Thank you all.
Thank you, Larry. Thank you, Gordon.